In this section we're going to continue on with hypothesis testing, but in particular we're going to talk about hypothesis testing with means. Now we're still going to follow through with the same steps to the p-value approach that we've always been using. The first step is to state HO and HA, your null and your alternative hypothesis. Second step is to state the level of significance, which is your Greek letter alpha. This is usually given to you in the problem. Third step is to calculate the test statistic. Now this is something new. This test statistic is a t value, not z, because I usually can assume normality, but I have a smaller sample size, or sigma is unknown, so I have to use s. So my test statistic is to take x bar minus mu. Mu comes from my HO and HA, divided by s over the square root of n. This is distributed as a t distribution with n minus 1 degrees of freedom. So our new test statistic is important to keep track of there. Next step is we'll make a decision. Actually, not make a decision. We'll calculate our p-value. Now in order to calculate the p-value, we need to know two things. We need to know our test statistic, and we need to know the direction of the test from HA. Because this will tell me whether I'm right tail, left tail, or two-tail test. Once I calculate the test statistic, I'll make a decision. And remember, there's only one of two decisions I can choose. I can choose to reject HO, or I can fail to reject HO. These are my only two options. Now this is if p is less than or equal to alpha. Fail to reject if p is greater than alpha. And then my last step is to summarize your results in terms of HA. Now when we talk about in terms of HA, we're talking about in terms of the problem being tested. So those are still the same test steps we're going to use. The very last problem in this homework set goes back to the classical approach of hypothesis testing, and we'll look at that when we get to that problem. So let's go ahead and look at our first question. Okay, let's go ahead and read through the example to see what any information we can get out of this on our first read through. First of all, we have a simple random sample. A lot of times you'll see simple random sample abbreviated SRS. So if you see that notation, it means simple random sample. And we know it's been selected from a normally distributed population. So this is important to know. It says in a manual on how to have a number one song, it is stated that a song must be no longer than 210 seconds. So this seems like some important information. I'm not sure where it's going to come into play yet. A simple random sample of 40 current hit songs. So simple random sample is my sample size, so I know n is equal to 40 now. Has a mean length of 243.1 seconds. So that's x bar because it's based on a sample, and a standard deviation of 56.75 seconds. So this is s. Our level of significance is 5%, so this means alpha equals 0.05. It says use a 5% level of significance to test the claim that the sample is from a population of songs with a mean greater than 210 seconds. It kind of seems like it is greater than 210. 243.1 seems greater than 210, but we'll have to run through all the steps to see. So let's summarize what we have. We have x bar is equal to 243.1. We have our sample standard deviation is equal to 56.75. We have our sample size is equal to 40. We have our level of significance as 0.05. And I think we have one other piece of information, this 210 bit. And that 210 is going to go with my null and my alternative hypothesis. So I'll fill that in a minute. So let's go ahead and just follow the steps. 1. State HO and HA. Now we're using means here and not proportions, so I'm going to be using the Greek letter mu that represents population mean. And remember, HO is always equality. And then my alternative here, it says greater than. So if I'm looking at greater than, I would look for my greater than symbol, so greater than 210. Second is my value for alpha. That's given as 0.05. Third, I'm going to calculate my test statistic. Now remember, our formula for our test statistic is different here than it was in the last section. This is a t-distribution because sigma is unknown. So this is x bar minus mu s over square root of n. And we want to be careful how we put this in the calculator. So x bar, let's go ahead and scroll up and find our value, is 243.1 minus mu, and mu is equal to 210, all over s, and s was 56.75, divided by the square root of my sample, and if I scroll up I can see my sample size was 40. So again, we have to be careful how we enter this in the calculator. So numerator has to be in parentheses, 243.1 minus 210, close parenthesis, and then we're going to divide it by, and we have to be really careful about this. I need to make sure I have parentheses in my denominator now because I have two things going on here in terms of division. So I have 56.75 divided by the square root of 40. And again, be very careful about how you enter this because it can really influence what your score turns out to be. So I get 3.69 here. I'll go ahead and just round this to two places. So 3.69 is my test statistic. Next, I'll go ahead and calculate my p-value. Now for the p-value, I need to know a couple of things. First of all, this is a t-value, and it's based on, here's 40, so this is based on 40 minus 1 degrees of freedom. So I need my t is equal to 3.69. I need to know that my degrees of freedom are equal to 39, and I need to know this is a right tail test. So with all of this information, I should be able to calculate my p-value. Now we're going to run into a problem right away when we get started with this. We'll sketch up our normal distribution, or sorry, our t-distribution shape. My mean is at 0. Here's 3.69. My right tail test means greater than, so this is my area. So this is my p-value. Now this is the t-distribution with 39 degrees of freedom. Let's go ahead and pop up our t-tables. So copy of the t-tables. If you notice, there is not a 39 listed here. I get pretty close to 39, but not quite. So the value for 39 is somewhere in between these two. But if I introduce just a guess of what's in between there, I'm going to have error. So I'm going to have to use my calculator on this one. So let's go ahead and open up the calculator, do second DISTR, and we're going to go TCDF, which is option 6. Now our lower, if we look at our picture here, is 3.69. Our upper is just some very large value, like 100,000, some positive value. I think I have a million there, but we'll use a million, see if it'll take it. Degrees of freedom will be 39. And I get a very small number. This is in scientific notation. And so we'll have to convert that to our decimal form. Now, when we're talking about this particular problem, what we're really trying to get after is that p-value. So rounding is going to be really important here. So if I look at this in terms of scientific notation, this is 3.4168 times 10 to the negative 4. So to convert this to scientific notation, I need to move the decimal 4 places to the left because of the negative sign. So there's 1, 2, 3, 4, and this is my new decimal point. So my p-value is equal to 0.00034. Now, if I were to ask to round this to 4 places, I would call this point 003. But the directions for this problem, let's say round to 3. So if we round to 3 places, my p-value would be approximately equal to 0. And I've put in my answer as 0.000. So that's my p-value. Now again, I couldn't use my normal tables here because my normal tables don't list degrees of freedom at 39. Next thing I'm going to do is to make a decision. Remember, there's 2 decisions I can make. I can reject HO, And I'll do this if p is less than alpha, less than or equal to alpha, or I can fail to reject HO. And this is if p is greater than alpha. Well, for our example here, we have p equals 0.000, and our alpha that was given was 5%, 0.05. And the given value, we can see is right up here, is 5% from here. So clearly we have p less than or equal to alpha, because 0.000 is less than or equal to 0.05. So our decision here is going to be to reject HO. Okay, 6. We're going to summarize or draw a conclusion. So if we were to summarize here, first of all, we always blame it on the data. So the data supports the conclusion of the alternative hypothesis. So the data supports the conclusion. And if we look back from what we're asked to being tested here, is the data supports the conclusion that the sample is from a population of songs with a mean greater than 210 seconds. Because we rejected HO, that meant we had support for HA. Okay, and we can see that that information is all up here in the given. Okay, so again, it says, claim that the sample is from a population of songs with a mean greater than 210 seconds. So I just copied it basically from the problem that was given. Now we can also answer another question from here. So let's go ahead and pull in another question. And this isn't step 7 or anything, it's just an additional question here. But what do these results suggest about the advice given in the manual? Well, if you recall, the advice given in the manual said that the song must be no longer than 210 seconds. But we just took a simple random sample of, popular songs, and the average was 243.1 seconds. And we did a test of significance, and we found that the true mean is greater than 210 seconds for that example. So the results suggest that the manual, or the advice in the manual, is not good. Because we just did, again, like I said, a simple random sample of 40-some songs, and we found that the average was way over 210 seconds. So this is an example of a run-through. This is really exactly the same as proportions, except now our test statistic and the distribution has changed. Okay, in this problem, let's go ahead and read through again to see if we can get any information about what's going on and some sample values as well. So first of all, we know that our underlying distribution is normal, so that gives us a good start. A coin mint, this just means like the US Mint, like in Denver, has a specification that a particular coin has a mean weight of 2.5 grams. So this is what the expectation is 2.5 grams. So that's our population mean. That's going to take into account our HO and our HA. We have a sample of 39 coins, so this is our sample size. The mean weight of these 39 coins, since they're based on a sample, are X bar, and the standard deviation, since it's based on a sample, is S. This says to use a 1% level of significance, so that alpha equals 0.01. Now this is going to mean a population with a mean weight equal to 2.5 grams, so that's our value of mu again. So let's go ahead and start with HO and HA after we look at our summary values. So X bar is 2.49579. S is equal to 0.01166. We don't want to round here, because if we do, we're going to get inaccurate answers. And our sample size is 39 coins. we have our level of significance alpha is 0.01, 1%, and we have our mean here is equal to 2.5. Now, what we're doing is we're checking 39 coins from a very, very large batch. And we're trying to think, okay, is this coming from a batch of coins whose true mean is 2.5? So for the first test, we want to state our HO and HA. So we're looking at means. We have 2.5. Now, this says if we're checking to see if it's equal to 2.5, the alternative to that would be not equal to 2.5. Okay? And then we have alpha equals 0.01 for our second step. Let me label that with our second step because I think it's important to keep track of the steps. Step 3 would be to go ahead and calculate our test statistic. Now our test statistic is going to be a t-distribution because sigma was unknown. So let's go ahead and just write down what it is before we start. It's x bar minus mu s over the square root of n. So this is going to be x bar, which is 2.49579, minus my hypothesized mean always comes from HO, my null hypothesis, 2.5. And if we look at this, this is slightly under 2.5. So that's interesting. And then S is 0.01166. And then over the square root of my sample size, which was 39. So let's go ahead and calculate this and see what we get for our value for t. And again, you have to be very careful how you plug this in, because just with a misplacement of parentheses, we could get a wrong answer. So here we have 2.49579 minus 2.5. Close parenthesis. Now we need to open these parentheses up again because I want it divided by all of this. 0.01166 divided by the square root of 39. And we'll arrow out and close that parenthesis. Okay, so this gives me a t-value about negative 2.25. And I'll just round it to 2 places, but remember in my math lab you should always double check to see what the rounding instructions are. So this is negative 2.25. That's our test statistic. Step 3, calculate the p-value. Now to calculate the p-value, I need a couple of things. I need my test statistic. I need my degrees of freedom. My degrees of freedom in this case are going to be 39 minus 1 because my sample size is 39. So my degrees of freedom will be 38. And this is a two-tail test. And the reason I know that it's a two-tail test is I come up here and I check my alternative hypotheses, and since it's not equal I have 2 options, greater than or less than. So that's a two-tail test. So we draw out our t-distribution. The mean is 0. This is the t-distribution with 38 degrees of freedom. And here I am at negative 2.25. So p-value is getting a value as extreme or more extreme. So I'm looking in this right tail. But because this is a two-tail test, I have to double this area. So this area is half of my p-value. Let's go ahead and use our calculator to find this one. We can actually use our t-tables on this as well, and we'll show that in a second. So we go second, DISTR, TCDF is option 6. My lower is going to be, this is heading out toward negative infinity, so negative very large number. And then my upper is negative 2.25. Then I need my degrees of freedom, which in this case was 38. My last problem was 39, this one's 38. And then I can go ahead and find that area. That's a very, very small area. Now remember, this isn't my final answer because I still need to double that. So this is going to be half of my p-value. So this was 0.01516, we'll say, just for rounding purposes. My true p-value is going to be 2 times this. And I'm going to carry it out all the way. And then the easy part here, if your calculator, since this is your last number, I can just hit times and it takes the number from the line above, times 2. And I see that my true p-value then, since this is a two-tailed test, I had to double it, is 0.0303. So again, if they asked me to round to 2 places, I'd do 0.3. If they said 4 places, it's 0.303. So for this one, I'm just going to take it out to 4 places. Now I don't want to round before I get there, because if I do round too far ahead, then I'm going to get an incorrect solution. So my p-value here again was 0.0303. Okay, now how could we use our t-tables? Well, our t-tables, I need to know my degrees of freedom, and that was 38. Let's make this table a little bigger. So here's my 38 degrees of freedom. So right here. And I have negative 2.25. So I would like to look through here, and I'd like to get the closest I can to 2.25. I think it's somewhere in between 2.024 and 2.429. So the best I can do for my p-value using the tables is it's between these two values. Now if I look up here, that tells me my p-value is somewhere between 0.01 and 0.025. And that's the best I can do. And the best I can do then is to double that. So our t-tables can kind of help us out here, but they don't give me very accurate information. So I think it's better to go with our calculator output from here. Now once I have my p-value, my next step is to make a decision. Now remember, with my decision I only have 2 options. I can reject HO, and that's if p is less than or equal to alpha, or I can fail to reject HO, and that's if p is greater than alpha. Well, our p-value is 0.0303, and my alpha was 0.01. Now remember, the alpha was given to us. It's not anything I calculated. It was given to us in the problem, so using the 1% level of significance. Okay, well, I can clearly see here that 0.0303 is greater than 0.01. So we have p greater than alpha here, which means I need to fail to reject HO. That's this case up here, fail to reject. Then I'm going to summarize. And remember, I always blame it on the data. So the data does not support the conclusion. Now remember, this is always in terms of HA, so let's go look at HA again. The data does not support the conclusion that the average weight of the coins come from a population different from 2.5 grams. So the data does not support the conclusion that this sample is from a population with a mean different from 2.5 grams. So basically what that's saying is this supports that comes from a population whose mean is 2.5 grams. But our summary always has to be in terms of HA. Okay, let's go ahead and answer one other question about this. Now again, this isn't part 7 or anything, it's just a little extra question. Do the coins, the sample coins that we picked, appear to conform to the specifications of the mint? Well, it looks like to me that we have to look at the specifications first. Now the specifications were the average weight is 2.5 grams. Well, we just did this hypothesis test that said, oh, the average weight doesn't seem to be different than 2.5 grams. So do the coins appear to conform? Yes. Because their average weight appears to be from a population that's equal to 2.5 grams. So again, these are all different ways that we can answer and work with those types of questions. Now the last one that we're going to do goes back to the classical approach to hypothesis testing. So this is not using p-values. So I think it would be good to review the steps for the classical approach to hypothesis testing before we do this problem. So quick review. So steps to the classical approach to hypothesis testing. So some of the steps will be the same, some will be a little different. First step, state your null and your alternative hypothesis. Second step, we need to know the critical value, or sorry, state the level of significance. And that's going to be equal to alpha. Third step, calculate the critical value. And this critical value that we're going to calculate is going to be based on alpha. Fourth step, calculate the test statistic. Now the problems that we're doing in this section have the same test statistic as it did for the p-value. So this is going to be equal t equal x bar minus mu s over the square root of n. And this is going to be distributed t n minus 1 for our degrees of freedom. Okay, then I'm going to make a decision. And there's only two decisions I can make, is to reject HO or fail to reject HO. But I can't base this decision on the p-value anymore. So if I reject HO, it's because my test statistic is more extreme than the critical value. And so this would be the test statistic less extreme than the critical value. And we don't know if we're saying greater than or less than yet because we don't know HA. Okay, after I make my decision, I will go ahead and summarize in terms of HA. Blame it on the data. So this is in terms of the problem. Okay, so this should be kind of familiar. We looked at this and we had the hypothesis testing overview. So let's go ahead and look at some data and use the classical approach to hypothesis testing. Okay, for this problem, because we're given raw data, we're going to have to remember how to use our stat lists. But before we get started with that, let's go ahead and read through the problem. It says the world's smallest mammal is the bumblebee bat. Shown below are the weights in grams from a sample of those bats. Use the classical or traditional approach to hypothesis testing at the 5% level of significance, so this is alpha equals 0.05, to test the claim that these bats come from the same population having a mean equal to 1.8 grams. So this is telling me that my mean population is 1.8 grams. So this will have to go with my null hypothesis. Now, all of this, I can figure out x bar, S, and my sample size. Now pretty easily, 3, 6, 9, 12, 15, I can see my sample size is 15, but the rest I'll want to use my calculator for. So let's go ahead and open up our calculators. We're going to go to Stat, Edit. Now if you have some old data in here, remember you just go up and hit Clear and Enter, and you'll clear out that list. Now go ahead and enter the data as you see listed. Now make sure when you get done that you have all 15 data points entered. This won't take too long, so I won't pause the video. But if you'd like to pause the video while you're entering your data to check my work, that's a good idea. So 1.54. Okay, and then we just keep going from here. Whoops, I better be careful on that one. It's 1.54, 2.23, 1.67, and then my last one was 1.59. Okay, so if we note here, my next data point would be 16, so that means I have 15 entered. Now to come up with my summary statistics, I go to Stat, Calc, One Variable Stats. I don't have a frequency list, I'm just working with L1. So we go ahead and hit Enter, and here are all my stats. So it looks like to me X bar is equal to 1.66 with the 3 repeating, and we'll figure out what to do with that in a second. And my standard deviation is 0.26919 and 0.26919,63348. Okay, so let's go ahead and look to see what we have. So the first thing we're going to do is state HO and HA. So we know mu equals 1.8 is what we're trying to test. And then our alternative, because we're trying to see if it actually comes from a distribution of 1.8 with the mean, would be not equal to. So it could be greater than or less than. 2 is our level of significance, and that was really the only number that we were given outright. The rest we had to calculate. Step 3 is where we find our critical value. Now this is where it differs from our p-values approach. This is the classical or the traditional approach. So the critical value is based on alpha equal 0.05. And the fact that I have a two-tail test. So I'm using a t-distribution here, don't forget. So my mean is 0. My degrees of freedom are 14 because my sample size is 15. So 15 minus 1 is 14. Now I need 5% split between two tails because this is a two-tail test. So I need 0.025 in my upper tail, and I need 0.025 in my lower tail. And it's because this is a two-tail test. If this was a single-tail test, I'd have all of that area of my significance in either the upper right tail or lower left tail. So now what we're going to do is we're trying to find this critical value, and whatever I have for the negative I'll have for the positive, so I have symmetry here. So let's go ahead and go after our t-tables for this one. I have 14 degrees of freedom, so I can come down here to 14 degrees of freedom, and this says I have 0.025 in one tail or 0.05 in two tails, so it's going to be this column. Area in one tail, area in two tails match my picture. And I have 14 degrees of freedom, so I'd have 2.145 as my value. So it'd be negative 2.145 or a positive 2.145. Now you can also use your calculator if you have the inverse t, or if you programmed it in. It'd be second DISTR inverse t. If you programmed it in, it would be under your program button. So the area here would be 0.025. Degrees of freedom we just talked about were 14. And we paste, and let's see what it gives us for a critical value. Negative 2.145 if we rounded it to 3 places. So the inverse t works just as well here. So let's review what this picture actually means. If I get a test statistic that falls in this unshaded region, this is called my fail to reject region. If I get a test statistic that falls above 2.145, I would reject HO. If I get a test statistic that falls below negative 2.145, I would also reject HO. So those are my decision rules. Okay, the next thing I would do is to calculate my test statistic. And again, my test statistic is based on the t-distribution because sigma is unknown. So I have x bar. Okay, let's go back up and look. X bar was equal to 1.663 repeating. And I'll just round that to 2 places. My mean is 1.8, and that comes from right up here in my HO. Now my S, that's going to be a tough one for me to remember, 0.269196. 0.269196. We don't want to over round because if we do, we'll get an incorrect answer in the end. Our sample size was 15. Okay, let's go ahead and plug this into our calculators. So again, parentheses in our numerator, 1.66 minus 1.8 divided by, and we have to have this in parentheses because we want this to be divided by the entire fraction, 0.269196 divided by the square root of 15. And then we would want to arrow out and then close parenthesis. Whoops, I got the same thing twice there. And so let's go ahead and paste that into our lecture. So we get a negative 2.01. Negative 2.01 for my test statistic. Okay, now what I basically do is I take this negative 2.01 and I compare it up here. Negative 2.01 would fall somewhere right about here, and we could see that that's in the fail to reject region. So on my next step when I make a decision, I'm going to fail to reject HO because the test statistic is not more extreme than either critical value. Okay, and then we'll have a summary in terms of HA. Now the summary that I want to talk about here then has to go back to the idea of did these bats come from a population having a mean equal to 1.8 or not. So when we talk about the summary, remember we failed to reject HO. So let's come up and look. HO, I failed to reject this, so it looks like it does come from a population that has a mean of 1.8 grams. So the data does not support the conclusion. Okay, now remember this is in terms of HA. The data does not support the conclusion that these bats, and this is kind of a double negative when you read through it. So the data does not support the conclusion that these bats did not come from the same population having a mean of equal to 1.8 grams. Because this is always written in terms of the alternative hypothesis because that's what we're testing. So if we want to back up a little bit here, we could also say the data does not support, and if we're writing in terms of HA, but if we always also wanted to summarize this, we would say, you know what, we don't have enough evidence to say that they came from any other population other than the one that has a mean of 1.8 grams. So these can be tricky sometimes about how we write those. And we did not find a p-value here, we just used the critical value approach, which is the traditional, or the, like I said, the critical value approach to hypothesis testing. So when you're working through this section, make sure you're on the lookout for this change on this last problem where we're not using p-values. If you have questions, please feel free to stop by my office. Come bring your questions to class or stop by the Math Center in the library. Good luck.